All right, good morning, everyone. So, hopefully we'll finish everything off today. If not, we'll just do a little bit tomorrow and then do some group exercises and talk about the exam, the fifth exam, and the final, because we have that coming up as well. I haven't looked at what day that is yet. We should probably do that, but we'll get there. So, let's remind ourselves what we were talking about here. So last time we were looking at image formation from spherical mirrors, and we were looking at the concave mirror. So far we did case number one, where case number one was, again, not all these people, when the object was placed outside of the radius of curvature. So that was when it was out here, and what we found was that the image formation was actually here, and it was inverted, so it was upside down, but it was real since all the light actually passed through it. So whenever we had it outside of R, the image formation was somewhere between R and F, and it was inverted and real. So now, what we're gonna do is put this guy somewhere between R and F. So, who's chatting? Oh, it's Wednesday the 9th. Thank you, Jake. So, good. So Wednesday the 9th. All right, so now we're going to put this guy here, and then again we're going to draw our ray diagram, and then drawing our ray diagram, we'll then see where that image is going to be formed in this case. So again, here we have 3 or at least 2 rays. So our first ray is the one we're going to draw, which goes parallel to the principal, hits the back of the mirror, and then gets reflected through the focal points. So this is ray number 1. Again, ray number 2 is going to be the ray which then goes through the closest focal point here, hits the mirror, and then gets reflected parallel to the principal. So it's going to be this guy going out in this direction. And again, ray number 3 is the one which would go and hit the back of the mirror, get reflected off at exactly the same angle at which it came in as. And then where, if I could draw a straight line, these 3 guys actually coincide with each other is the location of the image. So in this case, my image then should be somewhere outside of R. So in this case, it's going to be somewhere about here. So this is going to be my image. So good. So from here, we can then see that as long as our object is somewhere between the focal length and the radius of curvature, in this case, then our image has to be greater than R itself. So it's going to be somewhere outside, out in this region here. It's also going to be inverted, just like in the previous case, and it's going to be real. So this is that image formation. And then finally, case number 3, we're going to do the same thing. So here is my principal axis. Here is my mirror. Here's my radius of curvature. My focal point, which is halfway amongst the radius of curvature. And now all we're going to do is we're going to put this guy inside of the focal length. So now I'm going to put my object here. So for case number 3 then, use that one in yellow. So case number 3 here, S is going to be less than the focal length. Okay, so it's going to be inside of the focal length. So here we're going to do the same thing. Again, I'm going to draw ray number 1. So ray number 1 is going to hit the back of the mirror, get reflected then through the focal point. So ray number 1. Now, when it comes to this guy, doing ray number 2 doesn't really make any sense, because here it has to go through the focal point and then hit the mirror and get reflected off, but the focal point is behind it. So, I mean, we can still do it, but it's just a little weird. So here it's actually better just to draw ray number 3. So here, ray number 3, again, is going to hit the back of the mirror and then get reflected off at the same angle at which it came in as. Again, if I could draw a straight line, life would be great. There we go. There's ray number 3. So what you can hopefully see from my picture, since I can't draw a straight line, but that's okay, is that these 2 lines, again, are going to diverge away from each other, which means that if I'm looking out in here, so again, my eye is going to be situated somewhere here, I'm not going to see these 2 cross here. I'm going to have to ray trace these guys backwards. So if I ray trace these guys backwards, so if I ray trace this guy back where I think it came from, I ray trace this guy back from where I think it came from, where these 2 ray trace lines converge with each other is then going to be the location of our image. So for this one, our image is actually going to be back here. So we're actually going to see the image behind the mirror. In this case, it's going to have a very large magnification, and it's going to be actually upright. So here we find is that this image is actually upright. So it's in the same orientation as the object itself. But this is actually going to be a virtual image because, again, if I hold my piece of paper at the location of that particular image, nothing is actually going to be there. No light is going to pass through that, so there's not going to be an actual image formed on my piece of paper. So this is what we're going to call virtual. So in this case, we're going to find that our image is actually going to be negative, okay? So this thing is going to be behind the mirror. So this distance here is what we would call a negative image distance, okay? So these are the ray diagrams then for a converging mirror, or what we call a concave mirror. So now let's do it for the convex mirror. So the convex mirror is nice because we only have one option. So there's only one case. We don't have more than one case. So here, again, this is our principal. So we're going to be reflecting off the back part of the mirror. So on this side, this is going to be my radius of curvature. This then is going to be my focal points. Okay. So let's again draw our object. So I'm just going to put my object anywhere out here. So this is going to be my object. So here we're going to do the same thing. So again, I'm going to draw ray number 1. Again, ray number 1 is going to be the one that's going to go and hit the mirror. And then instead of being reflected through the focal point, since the focal point is on the back side, it's going to appear as if it came away from the focal point. So it's going to actually get reflected off in this direction. So it's going to hit, be reflected, but reflected going away from the focal point. Okay, so this is going to be ray number 1. Ray number 2 then is going to be the ray that would go through the focal point here. So in this case, it should hit somewhere about here. But again, since it's not going to actually go through the focal point, it actually is going to be reflected back in this direction, then parallel to the principal. So this is now ray number 2. For this one, I'm only going to draw these 2 rays. I'm not going to bother drawing the 3rd ray. Now, again, our eye is going to be somewhere out here. So here's going to be my eye looking at these reflected rays. But again, these 2 reflected rays are being diverged away from each other. So what my eye is going to do is ray trace these guys backwards. So this one is going to ray trace this guy backwards, again, appearing as if it came from the focal point. And then it's going to ray trace this one backwards, and it appears that it came parallel to the principal. So where these 2 cross each other, which is the 2 ray traced lines backwards, this is then the location of the image. Okay, so this is going to be my image. So for this case, again, what we can see is that the image will be upright. It will again be virtual, because again, if I put my piece of paper there, there's not going to be any image formed. And again, my image distance will be negative. Okay. So it's behind the mirror itself. In this case, it has a smaller magnification, so it's not going to be as magnified as in the previous case for case 3. So good. So these are our ray diagrams. So this is actually how we would determine where the image is going to be located, and we can actually measure the image distances and all that stuff if we were very precise. So here we would actually have to draw things using a compass, using a ruler, nice straight lines, do all that good stuff. But that's not very practical. So what we can actually do is we can actually determine a mathematical expression to find out where these images and things are going to be formed. And this is what we actually call the mirror equation. Now, the mirror equation is based solely off of geometry. The way that you can actually do this is you can use any one of these 4 cases. So for the convex, or these 2 cases for the concave, or the previous case that we saw last time. But any one of those, you'll get exactly the same answer. I'm not going to bother going through all the geometry, but basically what you find is that 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length. This is what we call the mirror equation, which is actually also the thin lens equation. So you guys have actually seen this before. So we can also define what's known as the magnification. I know how to spell. So when it comes to this guy, so the magnification is defined as m, which is then equal to negative of the object distance, or sorry, the image distance divided by the object distance, which is also equal to the image height divided by the object height. So here, this is my object height h, and then this guy here is going to be my image height h prime. So the negative sign here basically means if it's inverted or not. So when I write down h prime, if it's inverted, such as in case number 2 here, I would actually have to write down a negative h prime to make sure that it matches. And then here, if this thing is a real, it's going to be inverted, hence the negative sign, because I'll have a positive for s prime, a positive for s, which is going to make the magnification negative, which means it's inverted. But if s prime is negative, such as when it's virtual, then this guy is going to be upright. So I'll have a negative of negative, which makes this guy positive. Okay. So good. So to use this thing, it comes with a bunch of sign rules. So let's talk about the sign rules. Sign rule number 1. F, which is the focal length, is positive if it is a concave mirror, and it's negative for convex mirror. So that's sign number 1. Sign rule number 2. The object distance will be positive if on the same side, which the light comes from. So for all of the cases that we drew down, in this case, S was always positive, and it's always positive because it's on the same side at which the light is coming from. Sign rule number 3, S prime will be positive if on the same side which the light is going to. So here, this is a negative S prime because here the light hits and reflects, and the light then starts on the left, goes to the right, but then ends up back on the left because now it's moving from right to left. So anywhere out in this region then where the light is going to, that would be a positive S prime. But if it ends up on this side, then it has to be a negative S prime. So here, this is a positive S prime because the light is going to, so it's coming from the right to the left. So it's on the same side of which the light is coming to. But this one then is negative because the light is going to the left, but the image itself is on the right. So this would be a negative S prime. And again, just to remind you of our conventions here, this distance is S, so that's the distance from the object to the back of the mirror. F is the distance from the back of the mirror to the focal point. And then S prime is the distance from the back of the mirror to the location of the image. Okay, so this is S prime. So good. So this is what we call the mirror equation. Again, mirror equation is just a mathematical way of determining. So this is 1 over S, the object distance, plus 1 over the image distance is then equal to 1 over the focal length. Again, if I have a converging lens, this is the positive focal length. If I have a convex mirror, then this is going to be a negative focal length. So let's do a couple examples of this, and let's just see how this thing works. So let's look at the first one. So the first one says we have a 1.5 centimeter tall diamond ring is placed 20 centimeters from a concave mirror with a radius of curvature of 30 centimeters. So wants us to determine A, the position of the image, and then B, its size. So let's draw our picture here. So good. So here we have a concave. So we know this is our concave. There we go. So one thing we're always going to do is first by starting off drawing our ray diagrams. So when it comes to the exam on Friday, part of the question will always be draw your ray diagram. So I'm going to give you free points for drawing your ray diagram. So life will be great. Okay. So good. So here, let's call this our radius of curvature R. This is then our focal point. So we're told that our radius of curvature is equal to 30 centimeters, which means our focal length is then equal to 1/2 of the radius of curvature, which is then equal to 15 centimeters. So remember, this is always true for a spherical mirror. Now we're also told that the diamond ring is placed 20 centimeters in front of the mirror, which means our object then, so if this is 30, this is 15, then it's placed somewhere about here, right? So this is my diamond ring. Okay. And we're also told that the diamond ring H is equal to 1.5 centimeters high. So this is our our object height. So good. So first things first, let's go ahead and draw a ray diagram. So we already know it's going to end up somewhere out here, but let's go ahead and draw a ray diagram again anyways. So again, ray number 1 is going to be the ray which hits the back of the mirror, gets then reflected through the focal point. So that's this guy. This is ray number 1. I'm going to draw ray number 2. So ray number 2 then is going to be the ray which goes through the focal point, hits the mirror, and then gets reflected off in this direction. If I knew how to draw, my life would be a little bit better. There we go. Should be somewhere more out here. So this guy should be somewhere out in this region, even though I drew a terrible picture, but this should be the position where it should be. So good. So let's look at number A first. So A then says, find the position at which this is going to be. So we're going to use our mirror equation, which says 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length. So from here, what I want is the image distance. So I'm going to subtract this term over here. So I'm going to get 1 over my image distance is equal to 1 over my focal length minus 1 over my object distance. From here, let's find a common denominator. So it's going to be F times S. So I'm going to get an S minus F divided by S times F. Finally, invert this. This then tells me that my image distance then is going to be equal to the object distance times the focal length divided by the object distance minus the focal length. So good. Plug in our numbers. We get in this case then is this is going to be 20 centimeters times 15 centimeters divided then by 5 centimeters. Okay. So this divides with this. This gives me now a 4. So this is going to be what? 4 times 15. 4 times 15 then is 60 centimeters. So this is then going to be my image distance. So it's going to be 60 centimeters away from the back of the mirror. Part B, we now want to know its size. Well, to do its size, we have to first look at the magnification, because we know the magnification then is equal to what? The image height divided by the object height, which means that the size, the image height, then is going to be equal to the magnification times the object height. But we also know that the magnification is also equal to negative of the image distance divided by the object distance. So here, if I now use this definition for him, this becomes now minus the image distance divided by the object distance times the object height. So this is then the size of my diamond ring. So it's going to be equal to what? Negative 60 divided by 15, or sorry, that should be 20. Remembered my numbers wrong. 20 times then 1.5 centimeters. Right? Last I checked, 60 divided by 20 was 3, so this should be negative 4.5 centimeters. So that means that my diamond ring image is negative because it's inverted, and then the size of it is 4.5 centimeters. Is okay? Not too bad, right? Good. Let's do another one. So the next one then says, number 2, an external rear view mirror of a car is a convex mirror with a radius of curvature of 16 meters. Determine the location of the image and its magnification for an object 10 meters from the car. So in this case, we're assuming from the mirror itself. So good. So let's look at the next question. So this was example number 1. Let's look at example number 2. Good. So example number 2, it's saying that we have a rear view mirror, which is now a convex mirror. So this is my convex mirror. And then we know that this thing has a radius of curvature. Say that's out here. So this is my radius of curvature, which means it's a focal point on this side. This is my focal point. And here we're told the radius of curvature is equal to 16 meters, which means the focal length is then equal to half of that, which is then 8 meters. So if this is 8 meters, on this side this would be 8 meters, so 10 meters is about where the object is, so it should be somewhere about here. So then we're told our object is placed here, which is then the object distance of 10 meters away. Okay. So again, let's start off by drawing our ray diagram. So again, our ray diagram is my ray is going to come in parallel to the principal, hit, be reflected as if it came from the focal point, which means it's going to be reflected off in this direction. This is ray number 1. Ray number 2 is going to be the ray which would start here and then end up at the focal point. So it's going to go somewhere about here. But then it's going to hit and then be reflected back parallel to the principal. So this is ray number 2. And again, my job here now is to use my eye and ray trace these guys backwards. So I'm going to ray trace this guy parallel to the principal. And again, where these guys meet up, this is going to be the location then of my image. So this should be my image distance, S prime. So good. So from here, I can see that S prime then is going to be negative, and it's going to be somewhere less than the focal point. So in this case, it has to be less than a negative 8 meters, basically. So it's going to be somewhere between 0 and negative 8. Okay. So good. So first, let's find out the distance. So again, we have 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length. But in this case, since this is a convex, according to our sign rules, this guy has to be negative. So I'm going to go ahead and insert a negative sign here. Okay. So this negative sign here comes from the fact that this guy is a convex lens, or convex mirror, sorry. So basically, when I put in the focal length here, I'm going to use positive 8 since I already put in the negative sign here. Okay. So I'm just a control freak sometimes, and I like to do it myself. So everybody's okay? Good. So again, we want S prime, so I'm going to subtract that term from over here. So I have 1 over S prime then is equal to negative 1 over F minus 1 over S, which is the same thing then as negative 1 over F plus 1 over S. So again, find a common denominator, that's S times F. So I get a negative S plus F divided by S times F. And finally, invert this guy. So I get S prime then is going to be equal to negative SF divided by S plus F. So object distance times focal length divided by object distance plus focal length. So plug that in and it becomes a negative of, so I get 10 times then 8 divided by 18, right? And this all has units of meters. Good. So this is what, 80 divided by 18. So it's close to about 80 divided by 20. So it should be a little bit greater than 4. So this is going to be something like negative 4.4 meters. Somewhere around there. Good. Magnification, let's do that over here. Magnification we know is equal to what? Negative object distance, or sorry, negative image distance divided by the object distance. So it's going to be negative of a negative 4.4 meters divided by 20 meters. So this thing is then going to be what? So this is going to be about what? 0.22? Is that right? Yeah, and move that over by 1. Yeah, so about 0.22. This is positive because it's upright, and it's 0.22 because in this case, what it's saying then is it's roughly about quarter of the size of the object itself. Okay. And again, just to check here, we said that this thing should be somewhere between 0 and negative 8, and then we got negative 4.4, so that matches what our picture shows us. And again, this thing is saying that it's roughly about quarter of the size. And again, if I was careful and I drew this thing properly, then yeah, I could see that this thing is somewhere about quarter of the size. But again, just drawing rough diagrams here. Everybody's okay? So not too bad. So these are spherical mirrors. So spherical mirrors, life is great. Everything comes down to basically 2 equations. So I have the mirror equation here, and I have the magnification, and everything is based off of those with these 3 side rules. That's about it. So these are spherical mirrors. So good. So the next thing we're going to look at is what you guys did in lab, which are thin lenses. So what's a thin lens? Well, a thin lens can come in all kinds of different shapes and sizes. So for example, I can have something that looks like this. I could 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 have something that looks like, I don't know, let's do something else. Blah, something really big like that. I can have all kinds of different shapes, right? So a thin lens is a lens that, if we define the thickness, so the thickness of the lens is this guy here, so how thick it is. A thin lens is defined specifically that the thickness is less or much, much less than the radius of curvature. Now, technically, each one of these that I drew has a different radius of curvature, and we'll talk about that in a little bit. That's what's called the Lensmaker Equation. But here we're going to pretend that the radius of curvature on each side is basically the same. Okay? So all we're assuming here is that these things are thin in the width or the thickness of it compared to the size of the radius of curvature. So if I do that, basically most of these lenses come down to one of two types of lenses. So in general, we have either what's called the converging lens or what's called the diverging lens. So pretty much all lenses are going to be defined in terms of one of these two. So for converging lens, I'm simply going to draw this guy. Ooh, not like that. That was horrible. So we'll try that again. There we go. So converging lens, I'm pretty much going to draw something like this. And then for the diverging lens, will look more like the second one here. So it's going to be something more like, wow, I cannot draw right now. Let's try that one more time. There we go. That looks a little bit better. So this is going to be our diverging lens. I'm going to draw it basically this way. I think I talked about this in the video for the intro, but I'm going to talk about it again. So basically what a converging lens is if I took light from a very far source, something like the sun, and I shine it parallel to the principal axis, which is what this guy is, what happens then is all the light then is going to pass through a particular point, which is called the focal point. So basically all of this light here is converged to pass through a single point, which again is called the focal point. So this is my focal point, where all that light gets shined through. So this is called converging because it converges all of these rays to a single point, which then allows me to kill an ant. That was good. So what about a diverging lens? So a diverging lens is, if this is my principal, then in this case, again, if I take light from a very far away source, do something like the sun again, and I shine light again parallel to the principal axis, what will happen in this case then is these lines don't converge anymore, but they actually diverge, and they all diverge away from a given point. So they all seem to have come from this point back here, which again is called the focal point. So all these rays here get diverged away from this point, which again is our focal point. Good. So again, pretty much all these lenses, they can all be classified as one of these two. So either the converging lens, where again all the light is converged to a single point, or the diverging lens, where it all diverges away and seems to have come from a given point. Now, most optical instruments that you're going to look at, so things like telescopes and microscopes and all these kind of fun things, are all typically combinations of these particular lenses. So sometimes they use two converging, sometimes a converging with a diverging, but it just depends on the type of optical instruments. So pretty much we want to do the same thing that we did last time. Let's look at our ray diagrams. So let's talk about how we actually draw a ray diagram with now our lenses. So let's first look at a converging lens. So here's my converging lens. So this time I'm not going to draw all the different cases like I did with the mirror. I'm only going to draw basically one case and then just to kind of show you how it works. So the way this works is a little bit different than from the mirrors where we actually have now two focal points, right? So there's going to be one focal point on this side and one focal point on this side. Just basically means if I was shining light through on this direction, it would be focused onto this side, but if I shine light going in this direction, it would be focused onto this side. Okay. So let's just go ahead and draw our object somewhere out here. So let's say here is my object. Okay. So again, we're going to have the same notation as before. So I'm going to define the object distance as the distance from the center of the lens to the location of the object. So this is my object distance. So here is going to work fairly similar to before. So ray number 1 is going to be the ray which goes parallel to the principal, hits the center of the lens here, and then gets refracted, or down then through, if I could draw a straight line, there we go, through the focal point on this side. So this is ray number 1. Okay, so it goes parallel to the principal until it hits the center portion of the lens. There we go, close enough to a straight line. That was horrible. Anyways, and then gets refracted then through the focal point. Ray number 2 is going to be the one which goes through the focal point on the near side, hits the center of the lens, and then gets refracted parallel to the principal. So this is ray number 2. So again, this one comes down through the focal point on the near side, hits then the center of the lens, and then gets refracted parallel to the principal. And then ray number 3 is the one which goes directly through the center of the lens, and then is refracted, but there is no deflection of the ray. It just continues to go in a straight line. So this one is going to come through, pass through the center of the lens, keep going here, and then come out on this side. Okay, so this is then ray number 3. Actually, kind of impressed with that ray. It was almost straight, so we're pretty good. Okay. So good. So this is how I would draw a ray diagram then for converging lens. So again, I would first draw ray number 1. That would then pass through here. Ray number 2 would then come down through the near side, get refracted parallel to the principal. Ray number 3 again would go through the center and come out through. And again, where all 3 of these rays converge with each other, that then is the location of my image. So this would then be my image. So again, we would define the distance from the center of the lens to the location of that formation, which is then my image distance. And then this distance here from the center of the lens to the far focal point is then the focal length. So let's do the same thing for diverging. So let's do a diverging lens. So here, we draw this guy here, draw this guy here, good, and good. And let's draw a parallel axis, or our principal axis. And again, I'm going to have a focal point on this side and a focal point on this side. Okay. Same thing, let me just go ahead and draw an object somewhere out here. There's my object. So again, we have the same nomenclature. So the object distance, again, is the distance from the center of this lens to the location of the object. So good. So here we're going to basically do exactly the same thing. So what I'm going to do here is, again, draw a ray number 1, which goes, again, parallel to my principal. It's the center of the lens. But again, here, instead of going through the near focal point, it's going to diverge away from the close focal point here. So this is ray number 1. Good. I'm going to draw ray number 3. So ray number 3, again, is going to do the same thing. It's going to come here through the center of the lens and just keep going straight. Nothing's actually going to happen to it. So this guy's just going to go out in this direction. So this is ray number 3. Now, ray number 2 is going to be a little bit different. Instead of trying to go through the near focal point here, it's going to try to go through this backside focal point. So what it's going to try to do is come in this direction as if it's going to pass through this guy, right? So I want it to pass through him, going across here. So this guy is going to do something. Can't draw a straight line right now. See, that's what happens when I was all impressed with myself. There we go, close it up. And this guy's going to come through here. But what will happen here is, since this guy is diverging on this side, by the time it comes out through here, it's now going to come parallel to the principal on this side. So this is going to be ray number 2. If you can kind of see what's going on with all my terribly drawn lines here. There we go. Erase that so you can kind of see here. Good. So again, this line is going to come through here, try to go through this focal point on this side, but once it goes through the lens, it has to go parallel to the principal. Okay. So again, what's happening here is, on this side, my eye is sitting over here. Here, my eye is sitting over here. Again, this ray is being diverged away. This one's also going to be diverged away. So what I'm going to have to do then is, same thing as before, ray trace this guy backwards. So if I ray trace this guy backwards, where then the ray trace backwards of ray number 2, ray number 1, and the straight line of ray number 3 meet is then going to be the location of my image. So this is going to be my image location here. So this one is actually going to be in front of. So this one then is going to be S prime. So let's talk about the difference between these images. This image here is a inverted real image, and it's real because, again, the light is passing through it, because here the light is starting off on the left and moving to the right and continues to move to the right. So if I put a piece of paper here, this one would have light actually passing through it, where this image here is actually upright and virtual. And again, it's virtual because no light actually passes directly through it, because the light in this case is moving from left to right. So the light keeps moving to the right, but the image is on the other side of which the light is coming from. So this would actually be a virtual image in this case. But these are actually our ray diagrams. Now, again, just like for the mirrors, all we have to do is draw 2 of these. We don't have to draw all 3 of them. So whichever 2 is your favorite. So if you want to draw 1 and 2, or 1 and 3, or 2 and 3, whatever combination, doesn't really matter. So typically, I usually just draw 1 and 2, because I can never draw this line straight, so life is great. Okay. So this is how we do the ray diagrams. So again, here, I mean, we could do this over and over again, but again, we would have to make sure we bring a compass and a protractor and all kinds of stuff with us to make sure that we could actually measure these things. But instead, mathematically, we would come up with an expression, which again depends only on geometry, which again I'm not going to bother writing down for you, but this is what we call the thin lens equation, which turns out to be exactly the same as the mirror equation, which says that 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length. And again, the magnification, M is equal to negative of the image distance divided by the object distance, which is also equal to the image height divided by the object height. Which, lo and behold, is exactly the same thing as for the mirrors. So the nice thing about mirrors and lenses is exactly the same expression works for both of them. We don't have to do anything different for them. Here, this also has sine rules. The sine rules are pretty much exactly the same, but we'll write down the sine rules anyways. So sine rules. So here, the focal length is positive if we have a converging lens. Negative for diverging lens. Number 2, S is positive if on side light is coming from. So same rule as before. Negative otherwise. This is negative otherwise. Number 3, S prime is positive if on side light is going to negative otherwise. So if I go back to my pictures, so again here, both of these both have a positive S because they're unassigned that the light is coming from. Now, when it comes to a single lens, S will pretty much always be positive. So if I'm dealing with a single lens, S will be positive. But the next thing we're going to talk about is combination of lenses. That won't always be true. So sometimes it'll happen that the formation of the image is behind another lens, that you're trying to make that from, which means it's actually going to be negative in that case. So we just have to be a little bit careful with those, but otherwise that's okay. Here, this one has a positive S prime, because here it's on the same side of which the light is going to, where this one has a negative S prime because it's on the opposite side of where the light is going to. It's on the same side of which the light is coming from. So this one would have a negative image distance, where this one would have a positive image distance. This would be a positive focal length, where this one here would then be a negative focal length. Okay. So good. Let's do a couple examples of this, and then we'll hopefully talk about some combinations of lenses. So this then says, what is the position and the size of the image of a 7.6 centimeter tall leaf placed 1 meter in front of a 50 millimeter focused or focal length camera lens? So a camera lens has actually a converging lens. So let's talk about this guy. So this is going to deal with a converging lens. So this is example number 3. Good. So let's go ahead and draw our converging lens here. There's my converging lens. Horribly drawn, but that's okay. I have a focal point here, and I have a focal point here. So here what we're told is that this has a focal length which is equal to 50 millimeters. And basically what we're going to do is we're going to put some object here, way out here, where the object distance in this case is equal to 1 meter. Okay. So good. And we also know that this thing has a height of 7.6 centimeters. Good. So first thing we're going to do is same thing as before. Let's go ahead and draw a ray diagram. So here my ray diagram says that I'm going to draw ray number 1, which goes parallel to the principal, and then gets refracted down through the focal points. So that's this guy. And then ray number 2 is going to come from here and then go through this point here. So he's going to go very slightly through this close focal point, hit then the center of the lens, and then go parallel to the principal off in this direction. Okay. Again, where these guys meet, this is going to be the location of my image. So this is my image. So this distance here is going to be my image distance. Good. So from here, we should have 2 things to be true. Number 1, the image distance should be positive, and the magnification should be inverted, so it should be negative, and it should be something very small. The size of this is going to be very small compared to the size of this guy. So good. So let's look at part A. So where is this guy formed? So we know S prime then is going to be equal to S times F divided by S minus F. So this is the same thing we did in 2 problems ago for the converging lens. So good. Let's plug in our numbers. We know this guy is 1 meter, and this guy is 50 millimeters. So it's going to be 0.05 meters, right? Divided by 0.95 meters. Okay. Assuming I did bad math in my head correctly. Plug in our numbers, what we find in this case then is this thing works out to be about 5.26 centimeters. So this should be S prime. Part B, we now want to know what is H prime. Well, again, from 2 problems ago, we know H prime is equal to M times H, which is also equal to negative S prime divided by S times H. Right? So this is going to be equal to negative 5.26 divided by S, which is 1 meter, so that's 100 centimeters, times H. So this thing works out to be about negative 0.4 centimeters. Okay. So this is then H prime. Okay. Let's do another one. So we already did that one. So the next one is this little chart here. So this says we have an object O stands on the central axis of a thin symmetric lens. Fill in the following, that should be chart, not charge. I don't know why I put charge. chart. There we go. So basically what we're told is that the focal length is a positive 10, and we know the object distance here is 5, whatever units this is, and then from there we have to fill in everything else. So we need to find the image distance, we need to find a magnification, is it real or virtual, is it upright and inverted, and what type of lens is it? Is it a converging lens or a diverging lens? Now, from here, since the focal length we're told is positive, we automatically know this thing is a converging lens. So you remember that converging lens corresponds with a positive focal length, where a diverging lens corresponds with a negative. So automatically we know that this thing is converging. So let's go ahead and start filling out our chart. So from here, we know the type is then going to be converging. F was given to us. We know that's 10. We also know S is going to be 5. And we want S prime. We want M. We want real, virtual. And we want upright, inverted. So good. So to find S prime, we simply then have to use our lens equation. So we know that S prime then is going to be equal to S times F divided by S minus F. Okay. Again, we're using that because we know it's a converging lens. So here, this thing is actually going to be negative because what? S is actually less than F, which means down here, this is actually going to be negative. So this is actually going to be equal to negative 50 divided by 5, right? Which is then going to be equal to negative 10. Okay, good. So from here, we can then put in a negative 10, right? Yeah, okay. Everybody's okay? Magnification. So for the magnification, we know the magnification is equal to what? Negative S prime divided by S. So this is actually going to be equal to what? Negative 2, right? So should be a negative 2. Oh, sorry, a negative, So that becomes a positive 2. Sorry, positive 2, not negative 2. Good. Real or virtual. So in this case, from here, what we know is that what? Since the image distance here is negative, that means it has to be a virtual image. Right? So in this case, what it means is that it's behind the mirror or the lens, which means it's on the opposite side of which the light is going to, which means that this thing is virtual. And since the magnification is positive, that means it has to be upright. Okay? So this one comes from the fact that S prime is negative, and this one comes from the fact that M is positive. So anytime M is positive, this thing is upright. Anytime S prime is negative, that means it has to be virtual. So that's it. That's example number 4. Okay, so we only got a couple minutes left. So in that case, instead of starting combinations, let me bring up a group assignment. So let's talk about this one real quick. So this is the same idea. So here you have a chart to fill out, but this has to do with mirrors instead of lenses, but the idea is exactly the same. So here it says, fill in the spaces below for the 2 different mirrors. So here, the first one, you're told that you have a concave mirror, which has a focal length of 20 centimeters, and you're looking for the radius of curvature. You know the object distance here, so this should actually be, I change that, this should actually be S. This one should be S prime. So you're looking for S prime, and then also M, the magnification. Is it real, virtual, upright, or inverted? And then this one, you don't know what type of mirror it is. You don't know the focal length, but you do know the radius of curvature. So the radius of curvature, remember, is related to the focal length. So you also know the focal length because the focal length is half the size of the radius of curvature. So you know that's actually going to be a negative 20 centimeters, which means that this is actually going to be a convex mirror. So you actually already know those things. You don't know the object distance, but you do know the image distance. And then from there, you want to find the magnification. Is it real or virtual or upright or inverted? Okay. So nice and easy, not too bad. So good. So we just have 2 more things to talk about tomorrow. So tomorrow we're going to look at combination of lenses, which will work the same way as combination of mirrors as well. You actually already did this for the pre-lab for the refraction lab, for the lenses lab, but we'll talk about it real quick. And then the last thing is we'll talk about what's known as the Lensmaker Equation, which is how to deal with a thin lens like these, but have different radius of curvatures. So how do I deal with a lens that has something like this, right? So 2 which all look in the same direction, or something which is, say, flat on one side. So how to actually find a focal length for things like this. Okay, so this is going to be called the Lensmaker Equation. Once we talk about that, then we'll be all done with everything for the entire semester. And then we'll just review for the upcoming exam. So, is everyone doing okay? Hopefully, I try not to talk too terribly fast today, so it should be okay. Michael, can you put the slide with the lens side rules? Yes, I would love to. So let me do that here. Previous. There we go. Okay. Any other questions anybody may have? You doing okay? Good.
You haven't know when like the finals are gonna be around?
Oh yeah, Jake told us in the beginning. So Jake's more up to date on these things than I am. So according to him, it's going to be Wednesday, the 9th. So Wednesday, December 9th.
So like next week?
Next week, yeah. So 1 week from today, yeah. And I believe it should be from what, 9 to 11 a.m. is when it should be. So this will be our final dates. And we'll talk about that quickly tomorrow as well. I might actually make a video of that and post that as well, just to talk a little bit about it. So I don't talk about it for just 30 seconds. So it should be fine. Good. Any other questions anybody has? No? Okay. All right. So I said we'll finish up everything quickly tomorrow, and then we'll be done. Life will be great. So have a good day, everybody. I don't know why you two keep laughing at me, but that's fine. Okay. See you there.